Hello everyone, in this video we will continue talking about Brent method. In the last video we talked about how to use F0 and Fmin BND, and in this video we will use them to solve some practical problems. Let's see the first example. The Colebrook formula for determining the friction factor for turbulent pipe flow is typically taught in undergraduate fluid mechanics. The formula for the friction factor lambda depends on the size of the Reynolds number Re and the relative roughness of the pipe wall epsilon. For the Reynolds number larger than or equal to 4000, the flow is assumed to be turbulent, and the friction factor is obtained by solving this nonlinear equation, as shown here. If the Reynolds number is less than 4000, the flow is assumed to be laminar, and the friction factor is given by the explicit formula here, lambda equals to 64 over Re. Write a function file, friction.m, for which the input parameter is the Reynolds number Re and the relative roughness epsilon. The output parameter will be the friction factor lambda. Before you write your code, I will give you some additional information so that you can use them to check if your codes are correct. So 1 Re is equal to 10 to the power of 5. 1 epsilon is equal to 0.005. Lambda will be equal to 0.0313. And 1 epsilon is 0. The Reynolds number is still 10 to the power of 5. Lambda will be equal to 0.0180. So you can use these information to check if your codes are correct. Alright, then let's create the function file, friction.m. So the first line will be the function, and then output parameter lambda equal to the name of the file, friction, and the input parameter will be Re and epsilon. So this will be the first line. We can save it as friction.m. Alright, so you can see there are two different scenarios. The first one is the Reynolds number less than 4000, and then we can use the explicit formula to find lambda. Otherwise, when it's larger than or equal to 4000, we need to solve a nonlinear equation. So we can use if condition to deal with the different scenario. If Re is less than 4000, then the lambda can be directly calculated, will be equal to 64 over Re. Else, if the Re is larger than or equal to 4000, we need to solve a nonlinear equation. So we need to solve this equation to find the lambda. Okay, basically we solve the function f lambda, which is equal to lambda minus something in the bracket and to the power of -2. So this will be equal to 0. Then we use f0 to find the root of this function f lambda. So inside the bracket is -2 times log 10, and then bracket. Inside this bracket is 2.51 over Re times the square root of lambda and plus 0.27 times epsilon. Alright, so we need to use f0 to find lambda. So lambda equal to f0, and we first need to define the function. We call this f, and the initial guess, we can use 0.1 as the initial guess. You can try other values, and we need to define the function. The function is f. We can use at symbol x, and it's equal to x minus bracket to the power of -2. X minus bracket to the power of -2. And inside the brackets, it's -2 times log 10, and then bracket. -2 times log 10. There is another bracket. It's 2.51 over RE over square root of lambda. 2.51 over RE over square root of x. And then plus 0.27 times epsilon. Plus 0.27 times epsilon. Okay, so this will be the function, and then we can end this if condition. All right, so we can save it and then call this function in the main file. We can call lambda equal to friction. We can first try a Reynolds number less than 4,000. For example, it's 64. Yeah, we have 1 and 128, and we have 1/2. So it looks right. For the Reynolds number larger than 4,000, we can use the value 10 to the power of 5, and epsilon is 0.005. 10 to the power of 5, and this one is 0.005. Okay, so this works, and we can try another one. Epsilon is equal to 0. Then we have 0.018. Okay, so this is the first problem. And let's see the second problem. The total drag on an airfoil can be estimated by using this formula. D is the drag, sigma is the ratio of air density between the flight altitude and sea level, W is weight, and V is velocity. As seen in this figure, the two factors contributing to drag are affected differently as velocity increases. Whereas friction drag increases with velocity, the drag due to lift decreases. The combination of the two factors leads to a minimum drag. So question 1, if sigma is 0.6 and W is 16,000, determine the minimum drag and velocity at which it occurs. All right, so we know the value of sigma and the W. We want to find the value of V, and also which makes the D minimum, right? We also want to know what's the minimum value of D, okay? So we have a function so D is equal to 0.01 times sigma 0.6 V squared plus 0.95 over sigma 0.6 times W, which is 16,000 over V, and then square. So we want to find the minimum value of this one-dimensional problem. Okay, so let's see how to solve this problem. We can use f min b and d, which is a built-in function. So we first we need to define this function, right? So d equal to at v, and then it's 0.01 times 0.6 times v square and plus 0.95 over 0.6, then times square 16,000 over v. So this will be the function d, and we want to use f min b and d to find the minimum value. So this, the first parameter is v min, second is d min, equal to f min b and d So the first parameter is the name of the function, which is d, and then the the initial interval, which bracket the minimum. So as shown in this figure, we can start from 0, and the maximum is 1200. So we can use 0, then 1200. All right, so let's see. Okay, so the minimum value of v is 509.8181, and d mean is 3.119 e positive 3. Okay, so this will be the result for the first question. So let me save it in a file. So these two lines will be the problem A. All right, so let me save this as question 2A. And then this one as question 2B. Question 2B. Okay. So the problem B, in addition, develop a sensitivity analysis to determine how this optimum varies in response to a range of W values from 12,000 to 20,000 with the sigma equal to 0.6. So we need to find, we need to use F min B and D for different values of W in the range of 12,000 to 20,000. So we can create a vector for the different W values in that range. So we can create a vector W from 12,000 to 20,000 with a interval, for example, 1,000. Okay, so this will be the vector W, and the sigma is a fixed constant 0.6. Then we can use F min B and D for each value of value of W. So for I from 1 to the length of W, we perform this F min B and D. We find D, the V min and D min. So each time we will find a value, so we need to have the ith element F min B and D. So each time we will call this function, we need to use ith symbol. It's V, and it's 0.01 times sigma times V square and plus 0.95 over sigma, and then times the W over V square. So this W will be the ith element of W because it keeps changing over V. So we need to have first the lower bound of the interval is 0, the upper bound is 1200, right? So this will be the F min. And after we call this F min B and D in the for loop, we will get a series of V min values and series of D min values for each W, right? If we want to do a sensitivity analysis, we can plot the V mean values and the D mean values versus W. So W V mean and W D mean, and we can use, for example, the blue curve for the first plot and the red curve for the second plot. Okay, so let's see. The line for, okay, so here. All right, so this will be the plot for the sensitivity analysis. So you can see this is how the V mean and D mean changes with different values of W. The results indicate that the minimum drag is almost linear for the specified range of W. Okay, so this is the second question. All right, so let's see the quiz problem. So this time we have two problems. The first one is real mechanical systems may involve the deflection of nonlinear springs. As shown in this figure, a block of mass m is released a distance h above a nonlinear spring. The resistance force F of the spring is given by this function, and this function is a nonlinear equation, and conservation of energy can be used to show that 0 equal to these terms, and solve for D given the following parameter values. So K1, K2, M, G, and H are all given. You need to solve this nonlinear equation, solve for D. And you can use F0 to solve this problem. You need to come up with a reasonable initial guess. It can be a single initial guess or two initial guesses that bracket a sign change. So this is the first problem. You can use F0. Let's see the second problem. Roller bearings are subject to fatigue failure caused by large contact loads F, as shown in this figure. The problem of finding the location of the maximum stress along the x-axis can be shown to be equivalent to maximizing the function fx. So fx is shown here. It asks you to find x that maximizes fx. So maximizes fx equal to minimizes negative fx, right? And then you can change this maximization problem to minimization problem, and then use f min b and d to solve it. You need to come up with the initial interval that brackets this this optimum. So you need to try different initial interval to make sure it works. So these are the two problems for the quiz. In the next video, we will talk about a new topic.